Hi, my name is Daniel Galron, and I'm an applied research scientist at eBay's New York City office, where my team focuses on building recommender systems. So in this talk, I'm not really going to go over frameworks. I'm not going to go over specific technologies that we use. Instead, I'm just going to talk about the process by which we went about building a deep learning-based recommender system that can scale to our production needs. So we're going to go over a lot of material in this talk, and I'm going to gloss over a lot of detail. I'm happy to dive into the details in the office hours following this talk. So deep learning is quickly becoming a vital tool in every data scientist's toolbox. Over the last 5 years, there have been groundbreaking improvements in applications like computer vision and natural language processing and other signal processing applications in information retrieval. So given the importance of deep learning, there's unfortunately been very limited information shared on how to actually bring deep learning systems to production scale problems. So in this talk, I'm going to share about some of the lessons that we learned in applying deep learning to building recommender systems at eBay. So I'm first going to talk about what problem we're trying to solve and why actually the recommender system problems that we have at eBay are among some of the most difficult ones in the industry. I'll then give a very brief high-level introduction to deep learning and talk about some guidelines as to when it might be an appropriate tool to apply to a problem. I'll then go into how to frame your problem as one that can be solved using deep learning techniques. And then some of the design decisions that we had to make in order to make the model that we built production performant. And finally, I'll briefly talk about how to evaluate your models in order to allow you to fail fast when developing. So what are we trying to solve? So eBay is a marketplace that connects buyers and sellers all over the world. I'm sure, how many of you have eBay accounts? Cool, what I would expect. Well, so at any given time, we have about 1 billion items that are live on site, and we have 150 million buyers and sellers. So because we're a marketplace and we don't actually hold our own inventory, we have some interesting constraints on our listings. So first, we have very limited structured data. So for each item that we have listed, there's always going to be a title and an image and a category for that item. Sometimes, but not always, we're going to have some key value properties of an item, like its brand, its model, its color, and so on. And then for some fraction of our inventory, we can map the items to a product catalog. However, by impression, a lot of the inventory we have has gaps in the structured data coverage. We also have a very volatile inventory. So oftentimes, items are only going to stay on site for less than a week because just they happen to be bought very quickly, which means that each item will get on average a very small number of clicks. Furthermore, a lot of our listings are single quantity, meaning that only one person can buy that item. The fact that our inventory is volatile means that we have very, very sparse behavioral signals on which we can build predictive models. And then finally, we suffer from the cold start problem. Because we have millions of new items listed every day, we need to be able to provide recommendations for those. And classical techniques don't actually help us when there's no pre-existing information, behavioral information about an item. So any recommender system that we build has to account for these challenges. It needs to be performant enough to provide recommendations for 1 billion items. It needs to be robust enough to learn from extremely sparse signals. And it needs to be applicable to newly listed items for which we have no behavioral signals yet. So the standard approach to building recommender systems is called collaborative filtering. Now, there are many flavors of collaborative filtering algorithms. The one that we're going to focus on today is called item-to-item collaborative filtering. The idea behind item-to-item collaborative filtering is to consider all people who have interacted with a seed item, so for example, the ratings that users assign to a movie, and then find a set of items that have the most similar ratings pattern to that seed item. That way, for example, if someone rated a movie highly, like Goodfellas, this technique is going to find movies that are also similar to Goodfellas by considering the ratings that the same users assigned Goodfellas assigned to the remaining candidate items. a common way of computing this rating similarity is by taking the cosine similarity between the ratings vectors of a movie, and then for a given seed item, rank the candidate movies by their cosine similarity to the seed. So to take an example, suppose that we want to find a recommendation for Goodfellas. We can compute the cosine distance between the ratings vector of Goodfellas and every other movie in the data set. The calculation sort of looks as follows. The thing to note is that sort of we're rewarded for movies that have similar ratings by the same user, and we are penalized according to the norms of those vectors. So like the more popular a movie is, the more it'll be penalized. Now, one thing to note is that in this case, we have explicit feedback, right? A user's rating of a movie. Oftentimes, we don't actually have that information, though. We'll only have implicit feedback, like which users viewed an item or which users purchased an item. That would then lead us to use cosine distance or cosine similarity on binary indicator vectors. So we'll get into that in a little bit. So these collaborative filtering methods work really well on a lot of problem domains where you can get dense enough behavioral indicators. Unfortunately, in general, this approach is really, really hard to apply at eBay due to the nature of our inventory. So the fact that most of our items are singleton items and can only be bought by one person means that when we apply cosine distance, it's not going to really matter because there's only one user who bought that item, and so the vector just doesn't have enough information in it. So another challenge, which we're not really going to address in this talk, is that implicit feedback is generally less reliable than explicit ratings, right? Our best signals of indicating user interest are binary signals, such as whether a user viewed an item or purchased an item. But they're not foolproof, right? Just because I click on an item doesn't actually mean that I like it or am interested in buying it. Now, one alternative that we could maybe use is to try to cluster listings into static entities based on some properties of the items and then perform entity-to-entity collaborative filtering. So this is actually what we've been doing for a while. But the problem is that this approach doesn't really scale in terms of quality, right? Because computationally, computing these clusters can be really expensive. And then from the amount of effort it takes to tune the hyperparameters and ensure that the clusters are granular enough to be useful for collaborative filtering is really, really hard to do. So let's briefly just consider what information we have about an item. We have its title. We have some properties, sometimes, like the brand and the color and the style. And maybe we can use that information to actually build a predictive model that can act as a recommendation model. So that's what we're going to try to do. We're going to try to build a machine learning model that can model the common behavioral co-occurrence patterns, like co-views and co-purchases between items, based on some of their content features, even when we have sparse behavioral signals. Cool. So that's the problem we're trying to solve. Let's actually go into what is deep learning and when should we use it. So in traditional machine learning workflows, you have some input data, like an image, and you as the machine learning practitioner writes code to extract features from this data, right? So for example, it might involve defining patches of pixels using some method to select which ones should be included as input to the model, and then training a classifier or a regressor on these features. The problem with this is that it requires a lot of manual effort to define exactly the right kinds of features that are optimized for the task, right? You can imagine that you have one task where you're trying to, predict, like trying to identify, an animal in an image, and then another task where over the same image, you want to, separate the foreground from the background, right? Those are two different tasks, and you would actually have to, you'd actually have to manually construct features separately for those tasks. That can be a really, really expensive process. So with deep learning, the idea is that the feature extractor is just another model, right? It's just another function that is parameterized. And the feature extractor can be trained end-to-end as part of the system. So instead of a manual pre-processing step. One way to think about this is that the trainable feature extractors learn a kernel from a raw input space to a higher dimensional space, or sorry, a more abstract feature space where the data is linearly separable. And it does so in an end-to-end manner where you can have your favorite optimization algorithm jointly tune the parameters of the trainable classifier and the feature extractor in order to maximize the loss of the classifier. Typically, the reason it's called deep learning is that the trainable feature extractors tend to be stacked, right? So you'll actually have a couple different extractors, one on top of the other, where each extractor basically takes the output of the previous layer and then transforms it in some way using its set of parameters in order to produce an output that then gets passed on to the classifier. So for example, in the case of images, you can have the first one be an edge detector, then that feeds into a shape detector, which feeds into like an object detector, and finally that feeds into your classifier. So that's all well and good, but how can this actually help us in collaborative filtering? So, earlier we said that we have some information available to us, like the titles of items, the properties, and the category, and these can be fairly descriptive of the functional and stylistic semantics of the items. So at a very high level, what we want to do is we want to aggregate behavioral signals, like co-purchases, across semantically similar items. So for example, if we have an item that's like a Harry Potter collectible, but it's a singleton item, meaning only one person can buy that, we want to leverage co-purchase data from some other semantically similar items, like other Harry Potter memorabilia, to enrich our behavioral signals. So one sort of question, though, is then how do you apply deep learning to the kinds of features we have, namely the text, right? So in our case, we have title tokens and key value properties, which we need to encode somehow for the machine learning algorithm to read. So one common way to do that is with one-hot representations. The idea is that we assign an integer index to each word in the vocabulary, like the tokens that are present in an item title, and we construct a binary vector to represent them. The binary vector would have the dimensionality of the vocabulary, and it would have a 0 in every position except for the index corresponding to the token that it represents, which will have 1. So for example, in this 10-dimensional vocabulary, this would be the binary representation for dog. And if we then wanted to construct a representation for a whole sentence, you could basically just take the element-wise OR of these vectors to get another binary vector with a 1 for every token that's in the sentence. Now, this is problematic, right? First of all, these are very high-dimensional vectors, and word vectors will have the length of the size of the vocabulary, which can be in the hundreds of thousands. If you want to encode n-grams, you're going to have a polynomial increase in the size of your dimensionality. And then the other thing is that with these one-hot representations, there's no way to encode semantic similarity, right? All words or all representations are equally distant from each other. So one of the very nice innovations in deep learning over the last few years, which allows it to be used for text data, is the development of continuous vector representations. So the idea is that each token is going to be assigned a d-dimensional vector of parameters. You can think of these vectors as a feature extractor, where each token is associated with d features. And then the vectors are just parameters in a neural network, so their values are set via your preferred optimization method. One of the most well-known examples of this idea is word2vec. Word2vec is a very shallow neural network. It's actually a 2-layer neural network that learns d-dimensional embeddings for items by maximizing the log likelihood of a word appearing in a given context. The idea is that because semantically similar words appear in similar contexts, in order to model the log likelihood, the feature representations or embeddings that you're going to learn are going to have to be similar for similar words. So in this artificial example, you would see that the vector representing dog and puppy are very close together in vector space. A little bit farther away are dog and cat, and farther away, dog and flower. So for those of you who haven't played around with word2vec, it's a really fun tool to play with. There's a nice tutorial on how to implement word2vec models in TensorFlow here. And you can actually download the word2vec software online. So how can we use some of these concepts to help us in recommendations? So we can learn embeddings for the information that we have, namely the title tokens and the key value properties. And then we can use those embeddings as input to a predictive model that predicts whether 2 items are likely to be purchased by the same user. All right. So returning to the question of when we should use deep learning, sort of some high-level sort of guidelines are when dealing with natural language or in other domains where you have high-dimensional sparse feature vectors, you can learn embeddings as part of an end-to-end machine learning algorithm. If you find yourself doing a lot of manual feature engineering, where sort of it's just too hard to encode all the semantics that you need the model to understand, it can be very useful to try to learn those automatically. Now, one caveat, though, is that deep learning models tend to be very, very data hungry. So you either need to have a lot of training data in the hundreds of thousands to millions of examples, or you can take a pre-trained model, for example, one of the many models that are available online, that you can then fine-tune on your own data in order to allow the model to adapt to the distribution of your data set. So we've had a brief introduction to some of the concepts in deep learning, and we think that we can use some of these concepts in building a recommender system. Now we need to figure out how to actually frame the problem of recommendations as one that can be optimized using a deep neural network. So to do that, let's take another look at cosine distance. So we saw earlier that one way of making item-to-item recommendations is to take the cosine distance of the ratings vector and either the ratings vector or the co-purchase vector between two items, and then sort according to the cosine distance. So let's take a closer look as to what cosine distance actually measures. So cosine similarity, specifically, measures the cosine of the angle between two vectors. Right? So it rewards vectors according to how many elements of those vectors match, while normalizing them by the product of the L2 norms of the vectors. Now, when the vectors are binary, there's actually sort of another, maybe more useful way we can think about cosine distance. So the dot product in the numerator between these binary vectors basically rewards two items for every time that there's a 1 in the same position of those vectors, right? In other words, in our case, if our co-purchase vectors are the users who bought an item, if there's a 1 in both positions, that means that the same user bought both items, right? And then it penalizes the distance according to the square root of how many 1s in the vector, right? In other words, how many times each item has been purchased. So what does this mean for us? So instead, we can interpret this as operations on sets, right? The vector S can be thought of as the set of all users who bought item S. The vector R is the set of all users who bought item R. And we can take the intersection of those two sets, which tells us how many people bought both items S and R. So the larger this number is, generally the more confident we are that R would be a good recommendation for S. Except for the fact that we normalize. So our normalization consists of the square root of the number of times S was purchased, or times the square root of the number of times item R was purchased. So this measure rewards item pairs S and R that are frequently co-purchased by the same user, but adds a penalty for S's and R's that are purchased very, very often independently of each other. So if S and R are purchased together very often, then it's fine, right? But if S and R are purchased together sort of infrequently compared to how often they're purchased individually, then we actually want to have a penalty for that. And that's what this measure gives us. So we would like our deep learning approach to do something similar. We want to define the objective function for our top-level trainable classifier so that we optimize the model to achieve sort of the same effect with its predictions, right? We want it to reward pairs that are purchased together more frequently while penalizing those that are very popular. So let's actually think about sort of the loss function that we would want to model. So a very common top-level classifier used in building deep learning classifiers is logistic regression. Binary logistic regression models predict the probability of a binary response variable, like a co-purchase, given the input features. So in our case, suppose that we define our input features as feature functions on our seed and candidate items. So From here on out, S is always going to be the seed item, and R is going to be the recommendation candidate item. Let's assume that these feature functions, phi, are actually automatically learned feature extractors as part of a neural network. And let's assume that it's going to embed our items based on their titles, their properties, and so on into a d-dimensional vector space. Then what we would want is we want to model the event that the same user will purchase both items S and R while penalizing those items that are very popular. So to train the models, to train the parameters of a logistic regression model H, and in an end-to-end fashion, the parameters of the entire neural network, including the feature extractors and so on, we minimize the negative log likelihood function, which basically measures by how much the distribution estimated by our model diverges from the observed empirical distribution of labels that we see in our training set. So we can rewrite that loss function by explicitly highlighting the term that applies to positive labels and the term that applies to negative labels, like so. So this first term here models the deviation between the true co-purchase item that we observe versus what our model predicts. And then this term represents the deviation for the negative examples. Now, in our case, the training data only consists of positive examples, right? The only thing that we know is the distribution of pairs of items that were purchased by the same user, right? We don't actually have any explicit negative examples, right? It's up to us to define that distribution from which we sample our negative examples. So the question is can we sample our negative examples in such a way so that we achieve the same sort of penalty that cosine similarity applies to popular items S and R? So we have two sorts of penalties to consider, right? The first is the normalization factor on the popularity of the seed item S. In our case, we want to rank candidates for a given seed, right? In other words, we have a user who just bought item S, and we want to be able to rank recommendation candidates, 1 through n, for a given seed. That square root of S is going to be constant for each seed, right? So we can actually just treat that as a constant and not worry about that. Then to sample our negative examples, we can sample proportionally to the square root of how many times a recommendation candidate was purchased. So what this does, the effect that this has, is that for every seed candidate pair in our training data, we're going to sample that candidate item as a negative example proportionally to how often it is purchased independently of the seed item, right? So what that does is that basically constructs a training set where for each positive pair S and R, we're actually going to sample square root of R negative examples. Now, it also happens that this objective function is the same as that for word to vec. It's the same objective function that the skipgram with negative sampling solves for. That's not by accident, and I'm happy to go into the details during the office hours later. So, to recap, there are a couple things we need to think about when devising a deep learning-based solution to solving a problem. Right? You need to understand and quantify the properties of the ideal solution to your problem, and then figure out how to use your loss function, your sampling strategies for your training data, and even your neural network architecture, even though we didn't go into that here, to achieve those same properties. Cool. So far we've discussed the objective function we're optimizing and how we devised the sampling strategy, but we actually haven't talked much about deep learning yet. So deep learning models can be very time-consuming, both to train and to use for inference. So the design of any deep learning architecture ought to take runtime performance constraints into account, as well as the quality of the model predictions. So just to give you a taste of this, let's consider the scale of the problem that we actually have to solve at eBay. So on average, we have around 4 million new items listed every single day. Now, suppose that for each item, we have a recall set of 1 million candidates. So let's assume that we just have some other system that for a given seed item gives us a list of candidates to rank. So what this means is that on a daily basis, our network is going to need to evaluate 4 times 10 to the 12 item pairs, which is a lot. Since there are some 86,000 seconds every day, that means we need to evaluate pairs at the rate of about 46 million pairs per second. So we want to build our model such that it would require the least possible amount of hardware to run and reach our performance target. So broadly speaking, there are 2 ways we can achieve the desired rate. Right? We can maximize how many item pairs we process at the same time, and we can minimize how much time it takes to evaluate a single pair. We can achieve these goals in a number of ways. Right? First, we can scale horizontally across machines. All items on eBay belong to a category, and the way that we select the set of recommendation candidates for each seed item depends both on the category of the seed item and the category of the candidates. We can shard the categories horizontally, meaning that each machine is responsible for computing the ranking for items within a set of categories. We can also try to maximize parallelism within the model. So by using specialized hardware, like a GPU that has many more processing units than a CPU, within the device, on the GPU card, we can actually execute the model in parallel on multiple item pairs, because the evaluation of each item pair is independent of one another. We can also try to make sure that the different components in the model can be run independently of each other. Right? So we can parallelize the application of sort of the independent parameters of the neural network on a single item pair. And then finally, we can use highly tuned GPU code in the form of different CUDA libraries to ensure that each mathematical operator we apply in the execution of our model is as fast as possible. So let's now go into how we can design our model to adhere to these principles. So recall that we want to model this probability that a seed item and a candidate item are both purchased by the same user, conditioned on the features of the seed and candidate items. Right? So what that means is that we can decompose our network into 3 subnetworks broadly. Right? We have the phi function that operates on the seed item in order to construct the feature representation of that item. We have the phi function that operates on the candidate item. And then we have the top-level classifier that uses those 2 as input in order to make its prediction. So let's first talk about the design of our feature extractor layers. So the input for the feature extractor for a given item is going to be the tokens in the title, the key value properties, and the category. So we're going to start by embedding each of the title tokens, property pair, and category into a d-dimensional dictionary. Right? One way to think about this dictionary is that it's just a matrix that has a row for each token in the vocabulary. And then you can either index into it, or you can take the product of the one-hot representation of a token and that matrix in order to retrieve the embedding for that token. And these, like we said before, these are just parameters like other parameters in the model that we optimize end-to-end. We then apply a pooling layer, and the idea here is that we want to combine the information present in all the title token embeddings in order to construct a representation of the title. We want to combine the information of the key value properties to construct a representation of the properties, and we have the category. Although in general there's only one category for an item, so whatever we put in here will basically be a no-op. Now, there are a lot of different ways to pool vectors together. There are a lot of different techniques that have been written about. You have things like max pooling. You can do something fancy and have a convolutional neural network or a recurrent neural network to take into account things like the position of tokens. we've gone with something much simpler, which is mean pooling. And what mean pooling does is it basically just takes an element-wise average of the embedding vectors and produces a d-dimensional vector, right? So if we have a title of 5 tokens, we basically just average those 5 vectors together to provide a d-dimensional vector. So we're going to do this for the 3 sets of data that we have, the title, the properties, and the category, resulting in 3 d-dimensional vectors. We then concatenate the vectors together to construct an item representation of dimensionality 3 times d. We then add a nonlinear activation function. So nonlinear activation functions are really, really important in, when building neural networks. The idea of the nonlinearity is to project the results of linear operations, like the ones that we did down here, into a nonlinear space, where what that allows us to do is it allows the model to learn parameters such that as a result of the nonlinear activation, the resulting vectors are going to be linearly separable. Finally, we add a hidden layer that acts to combine the information in the title vector, the property vector, and the category vector into a single representation. These hidden layers basically just involve a matrix multiplication, where the hidden layer has a matrix of dimensionality, whatever the size of the input is, by the size of the output. And then when you multiply the input vector by the matrix, you get a vector that's the size of the output dimension. And then we put that through another nonlinearity, which gives us our item representation. So to construct the end-to-end network, we're going to apply this architecture for the item embeddings to both the seed item and the recommendation candidate. So in our case, these 2 subnetworks have their own sets of parameters. So unlike in Siamese networks, which have shared parameters, we actually don't share parameters between these 2 subnetworks. The reason for this is a bit complex, but basically what we want to do is we want to ensure asymmetry in our predictions, right? We want to make sure that we give different outputs for someone who bought a seed item S and then a candidate item R versus someone who first bought R and then S. So the inputs of these 2 feature extractors goes to our top-level classifier, which is just a simple 2-layer neural network, which consists of a fully connected hidden layer and an output layer that's just a sigmoid function. So the sigmoid function basically takes a scalar value and projects it into space 0, 1, thereby forming a probability. So let's actually point out where we can take advantage of parallelism and carefully tuned CUDA libraries here. So each token embedding can be constructed in parallel. The mean pooling of the title tokens, the attribute tokens or the property tokens, and the category can be independent of each other. And then the way that there's a CUDA library called cuBLAS, which is an implementation of the BLAS API to run on GPUs, is very highly tuned, and it can exploit parallel computation when doing matrix multiplications for the fully connected hidden layers. So finally, the last thing to point out in terms of productionizing this is that there is actually some redundancy here, all right? So you could, in principle, run every seed candidate pair through this network, but that would actually be highly redundant, right? Because you would be computing the same feature extractor subnetworks over and over again for the same items, right? If we have to evaluate 1 million candidates for a single seed, it doesn't make sense to just keep recomputing the seed representation over and over again. So in fact, when we bring this to production, our implementation actually decomposes this network and runs the components separately. For each seed item, we're going to run the seed feature extractor. For every candidate, we're going to run the candidate extractor. And finally, we're going to construct the Cartesian product of the 2 sets of feature vectors to serve as input to the top-level classifier. So briefly, let's see what sort of performance gains we can get from this. So on a single GPU, we can construct the seed and candidate representations for about 40,000 items per second. In practice, we're going to cache the learned embeddings for the candidate items in a database so that we only need to run the feature extractor on that day's newly listed items, so those 4 million items. This means that we can construct the item embeddings in around 2 minutes. Now, the expensive part of the computation is in the top-level classifier, which can process about 900,000 item pairs per second on a single GPU. So in one day on a single GPU, we can evaluate around 7 times 10 to the 9 pairs of items. Now, given that we said we have 4 times 10 to the 12 pairs of items that we need to evaluate each day, if we then distribute those among 50 GPUs, we'll be able to hit that target. Cool. So to sum up, in order for the model to be efficient in production, some sort of takeaways are you want to design your network to maximize parallelism. In actually applying the network, you want to minimize your redundancy, and you really need to think about accounting for every millisecond of computation that your network will act on. So finally, we're going to talk about the right way to evaluate your model for the task that you're solving for. So generally speaking, the complexity of deploying deep learning models to production means that there can be a fairly high cost to evaluating a model online. So given the number of choices you have when designing deep learning models, or really any machine learning models, right, in terms of the hyperparameters that you can choose, in terms of things like learning rate, and in our case, dimensionality of different hidden layers, it's really important to understand quickly when a model does not work well. So the choice of evaluation measure is absolutely critical when developing deep learning models. So we said that we're building a classifier, right? So there's a few standard evaluation measures that you could use, right? You have the precision recall curve, and then you have the training error and loss curves that you get when your model is training. And those can be really useful for making sure that your model is training as you expect, right? That you don't suffer from problems like the exploding or vanishing gradient problems, or that your learning rate and decay rate are working well. So the first couple of iterations of our models failed, and we were able to detect that by noticing that the error was plateauing really, really early. Now, while these measures are useful to check that your training algorithm works, it's not necessarily useful for understanding how the model is going to perform once you apply it to a production system. Right? So in our case, we actually care about ranking candidates for a seed item. So we need to design a ranking measure that would allow us to evaluate this. So what we're going to do is we're going to build a held out validation set of, let's say, 200 seed items bought by users. What we're going to do then is we're going to select a true co-purchase item for each seed. We're then going to randomly sample 200,000 random items to serve as a recall set. We then run all the item pairs for all of the users. And then for each seed, we're going to figure out where in that ranked list does the true co-purchase lie, right? The closer it is to the top, the more confidence we can have that the model is predicting something meaningful. So once we actually construct this validation set, there are several ways to evaluate the ranking. Right? There are standard ranking functions like mean average precision, discounted cumulative gain, and mean reciprocal rank. But for our problem, they don't actually quite fit the bill because they either assume having different degrees of relevance or having multiple sort of relevant results in a ranked list. In our case, we only have one relevant result in the ranked list. So instead, we actually found it really useful to consider an average rank across the 200 seed items by averaging over the position of the true co-purchase in the ranked list. But instead of using the mean, which is highly sensitive to outliers, we decided to evaluate our models using the median. Having a median rank of 2, for example, means that 50% of our predictions are in the top 2 slots, right? Which is very good. So it's also really easy to interpret that result, right? Because then you can go to your business partners and say, hey, look, for 50% of recommendations, the thing that the user will end up buying, on average, in the top 2 slots. Especially because our recall set is so large and we have a very long tail, when using the mean, it's going to be much harder to actually interpret those results. And then finally, once you do bring your model to production, the way to test on real, the best way to evaluate it on is on real data. So in our case, we actually use both crowdsourced human judgment evaluations in terms of relevance, as well as A/B tests. Cool. So to sum up, deep learning can be a very effective tool in solving a lot of different data science problems in production. But it's really important to understand how and when to apply it and how to experiment with and evaluate models quickly to allow you to fail fast. So I hope this talk has helped illuminate some of these issues. Thank you.
Great. Is mic on? Thank you, Daniel. That was a great talk. While Laura gets set up, we probably have time for one question.
Hi, I was wondering about the last part, evaluating the deep learning method. So let's say you're looking at the precision recall curve and it's not what you expected.
Yep.
How do you then go and figure out which part of your pipeline is what you should be working on?
Yeah, that's a really good question. We have yet to figure out sort of like a set of rules for that. Mostly, at least in my experience, it's just to try to understand the problem that we're trying to solve and to understand the distribution of data. If you understand if you can come up with some hypotheses as to what the neural network is doing, you can then just test by swapping out different components of the neural network, by trying to understand like how the different parameters are interacting with each other, and going from there.